Wait, is that the one where you just like
compound after the
where there's a long way and a short way?
That's combustion.
That's combustion.
Oh.
Yeah, limiting reactant is one of the things gets totally used up and the other one doesn't.
So they
Now this doesn't actually say what is the limiting reactant, but that is implied in the question. How do I know that? I know that because I'm given information about both reactants. If you are given information about both reactants, it is a limiting reactant problem. Period. So you're going to write that up on the board as a rule.
But how would you go about getting, do you have to get the molar and milliliters into the same unit?
Yes.
How would you do that? How do you get
Okay. So you remember our workflow before for dealing with stoichiometry problems, problems where there's an equation.
Could we do like 50.00 milliliters times 1 liter over 1,000 milliliters? No, I mean ml. And then times 0.2.
Yes. Yes, you're on the right track. Hold on, I want to give some like overall general rules for solving problems. Cool. So remember we got this workflow. We've got like, if we have given information and desired information. If we're given grams, what do we do with that?
You go to moles and you go to moles and you go to
And
grams.
then you do, put it in moles again, and then into grams.
Precipitation reaction problems have the same kind of idea, except that we don't have grams. What we have is molarity and volume. I'm going to use that to get to moles. So molarity is grams, or nope. Molarity is moles per liter, and volume is in liters.
So you can find.
So molarity is moles over liter times volume in liters.
Oh, so the liters cancel out and you get
So
a
you
mole.
can't find the moles.
So if you've got molarity and volume, you can get to moles. And from moles, it's just a regular old stoichiometric problem. Thing to keep in mind is that ionic compounds might dissociate into more than one ion, right? So there are 3 OH minuses. No, there are 3. Well, yeah, we're looking for NO3. There are 3 NO3s in every one of these when they dissociate. So that's a thing to keep in mind. Okay? Yeah, let's solve this problem. Guys, it's so much time. Okay. In general, we've got a limiting reaction problem. Limiting reaction problem. What is our general for limiting reaction problem? Our general plan.
We want to find,
limiting reactant.
Yes, we do that.
we
Find
find the amount of moles they create in the reaction.
No, we find the
I don't know how it
smallest
works.
We have the
substance.
product.
Yeah, the smallest amount of product that would get produced from either one. Yeah? Yeah. Same deal here. Alright, so we're starting with 50 milliliters of 0.2 molar NaOH. And Tiffany, you had the right idea about what to do here. We've got 50.00 milliliters Oh my gosh, I'm gonna need more room. How far over can I go here to still be on camera?
You're not on the camera right now.
Ooh.
Do you want me to move it?
Let's do this over here. Can I go over here?
Yeah.
Thomas,
It's
the
a little
cameraman.
high. It's a little high, but.
Okay, well, whatever.
Ooh, what a
Sorry,
legend.
folks watching on camera.
Dabbles in everything over here.
Where can I do it? I don't know.
I can move it over here to the left.
Okay, we'll do it over here. Thank you so
Okay.
much.
No problem.
All right. So let's start with our NaOH. We have 50 milliliters of NaOH solution. Oh my gosh, we're running out of room so fast. We gotta leave some sig figs out here. What am I gonna do with that?
Convert it to liters,
Convert it to
which
liters.
is 0.05.
Yeah, it's 0.05, so it's times 1 liter over 1,000.
This is 0.200 m over 1 liter.
No, 0.2 moles per liter.
Wait, why is that?
So if I take
Oh,
the
because
volume
it's 0.2. Oh, yeah.
times the concentration, I get the number of moles of NaOH. Now actually, I don't even really care about the Na, right? I only care about the OH.
Why?
Because that's the only thing that's participating in my net ionic reaction over here. I only care about those OH minuses.
Wait, can you reword it?
I only care about OH minuses because the sodium is a spectator ion, it's not participating.
Oh, yeah, then we're just trying to find precipitate.
I only care about the precipitant, which is the only product I care about at all. So, if I want to get to moles of OH minuses, how do I do that?
You multiply by
1 mole.
one mole of
OH.
OH over Na. Yeah.
I'm going to break here. So, that's, what is that? How many moles do I have? Fifty times 0.2 divided by 1,000. Someone calculate.
It's 25 divided by 1,000. Oh, wait, no, 0.2. I don't know.
Yeah,
I don't have my calculator with me.
I won't. I
it'd be
don't.
like point.
Why is it
Zero.
0.2 moles?
Got it.
It's 0.2 moles per liter because that's the concentration. The concentration that was given to me in the problem was 0.2 moles.
It's 0.01.
Yeah. I'm not joking.
So we've got volume, we've got concentration.
Wait, it's not. Wait.
These were given to me in the problem. And then we gotta make sure this step seems unimportant, it's just a 1-to-1, but this could be important, so don't forget it. Could be, for example, that we're caring about these NO3 minuses, in which case it would be 3-to-1, it's totally different. Alright, we've got the number of moles of OH minus that I have. So I've gone from molarity and volume to moles. Now what?
Now we need to find the other one.
Wait, do we want grams?
I don't know what grams
No,
yet.
we don't.
We need to find
Just
FE.
find the other one.
I do need to find Fe. But before I do this, I have this many moles of OH minus. Is that going to tell me which one is limiting or
No.
not? What do I need to find? Moles of
FE.
product. Alright?
Moles of. Oh, the total?
Yeah, what I care about is I care about how much product I form. So remember, limiting reaction problems, we're going to find how many moles of product are formed if Fe is limiting, how many moles of product are formed if OH minus is limiting. Then I compare those two.
So do you do times like 1 mole of FeOH3 over 1 mole of, or is it 1 mole of 3? 1 mole of,
How many
Oh.
moles?
1 mole of OH.
How many moles of OH minus do I need to make FeOH3?
Oh, 3.
3. So if OH minus is the limiting ion, I'm going to make 0.0033 something moles.
Wait, I kinda don't understand the second step.
This step right here?
Yeah, this step, I don't know why you, so I know like the .01, but I don't know like why you timed it like this thing.
Why did I do this?
Yeah, why did you do this?
Because this tells me how many moles of OH minus I have in my solution. I mix the two things together.
Yeah.
However, I don't care about how many moles of reactant I have. I care about how many moles of product that much reactant can make. Why? Because I need 3 times as much OH minus as I do Fe.
So why do you have 3 moles of Fe, 3 moles of OH?
Because for every 1 mole of FeOH3, I need 3 moles of OH minus from my net ionic equation.
Oh.
3 moles of
So,
OH minus makes 1 mole of FeOH3.
so the
So if
result
I have,
is if you have 0.01 moles of OH, you are gonna have 0.0033 moles of FeNO3.
FeOH3, yeah, the iron hydroxide.
Oh, gotcha.
Yeah, gotcha.
So you're using the net formula, you're not using the original.
I'm just going to use the net a lot easier to deal with.
Okay. So every time when we have these kind of questions, we just use the net formula.
Yes. Precipitation reactions, net formula is the way to go. All right, that's half of it, halfway done.
Can we do the same thing for
Yep. Same process.
30?
So,
The questions on a test like this, they're gonna take super long, right?
yes.
Could we just like not have these?
Yeah, could you not like give these out on a test?
Oh,
If you know
Kevin
they're gonna
back-
be time consuming, you know,
Kevin can't see.
So in general, I actually ask these as parts. So on a test, I will generally not ask you a question like this. I will say, you mix together these two things. Part 1, what is the net ionic equation? Part 2, what is the limiting reactant? Part 3, how many moles of precipitate
This is
are
gonna be a
formed?
fun final, right, guys?
Yeah, it's gonna be awesome.
What is a nation?
Okay.
What did you say was the first question?
What is the net ionic equation?
Oh,
Part 2, what is the limiting reactant? And then you will be like, it's a limiting reactant problem. I know how to do those. And then you'll be like, part 3, what is the yield? And you'll be like, great, I'm already 3/4 of the way to the yield. And then I'll be like, part 4, what ions are left in solution? And you'll be like, But that's okay, let's figure it out. The
What?
spectator ions are left in solution, right? Cool. Alright, so, someone who hasn't spoken much, what I'm going to write, I'm starting with the Fe, NO3, the iron nitrate part of this problem. What am I going to write first?
30 milliliters.
30 milliliters, because that is how much of it I have. Times. I've got it in milliliters.
You want to put it to liters?
I want to put it to
So,
liters.
0.03.
Wait, you can do that? You can just multiply the denominator by.
Well, you're just converting milliliters.
Just converting it.
Oh.
Just converting it to times.
So,
Alright, now I've got liters of my reactant. Remember, molarity and volume decide what I want to get. I want to get to moles.
Then we add 0.125 moles
Times 125.
over 1
No.
liter.
0.125 moles per liter.
Do we only want to know what is it called? NO3. So would it be like 3 moles of NO3?
I actually don't care about the NO3 because the NO3 is a spectator ion.
Both
I
of
care
them are.
about Which one is the not spectator?
Oh,
The ion, yes. So,
so small mole of Fe over 1 mole of FeNO3.
we got this, guys. I promise.
Are we doing the
Are
lab
we
today?
doing lab now?
Are you kidding?
Let's at least figure out which one of these is the limiting reactant. We're so close. Alright, how many moles of Fe3 plus do I have?
0.00375.
So you solved that by doing.
So it's volume in liters times concentration,
Oh.
Times the
I was
number of
thinking-
irons.
When you wrote the FeNO3, and then I thought you were doing that divided by the rest of it. No, never
Oh,
mind.
no.
No, yeah, that
No.
makes a lot more sense now.
How about that?
Okay.
That fixes it. Alright, I've got 0.00375 moles of Fe. How many moles of product could I make from that?
1 mole of FeNO33 over 1 mole of Fe.
So OH is the limiting
Can we just like,
Not have these on the final?
The OH
Because
is
you
the
already
limiting-
asked me that, and I already said, nope, they're definitely on the final.
It was worth the second
Dr.
try.
Fisher, we'll bribe you with Quran.
What?
Whoa.
Quran will be in this class next year again. If you don't give us these questions on the final.
Wow.
Ouch. That kind of negativity is, I don't appreciate that kind of negativity. We can all do this.
I'm sure Quran.
I know this is rough. You know, it's a lot of stuff. With these calculations, like, they're all do this. And they're always follow the same format. So, if you're like, whew, I need a second, this video will be online for one thing.
Oh, thank you.
Since I made it. But just do some practice problems. Go through the practice problems in the book. They sometimes take a few times to get it. I know sometimes in class you're like, I'm overwhelmed. But do some practice problems. Take a deep breath. They always follow the same format. They're really in a lot of ways very formulaic. Okay, so if all of the OH minus got used up, I would be able to make 0.0033 moles of product. If all of the iron got used up, I would be able to make 0.00375 moles of product. Which one is the limiting reactant?
First one.
H.
First one. So, what is the yield in moles? How many moles of product do I make?
0.0033.
Yes, I make
Bingo.
0.0033 moles of Fe.
And then you just convert it to grams.
And then you just convert that to grams as your very last final step.
Okay.
Whew. So these are really just limiting reactant problems. The only hiccup is one, you're using molarity and volume to get to moles instead of grams to moles, but it's a straightforward conversion, it's just molarity times volume.
Wait, do we convert the 0.0033 moles of
Okay.
this thing to grams?
Yeah, then you convert it to grams. I'm not going to do that because I want you guys to do the lab.
Wait, so why do you want to choose the limiting reactant for this precipitate rather than the other reactant?
Because in this case, I don't know which of these two is going to get used up first. I'm mixing two things together.
Oh.
One of them is gonna get used up before the other one, but I don't know unless I actually do the calculations which one's gonna get used up first.
Okay.
Okay? Okay. I'm going to give you some practice worksheets for stuff if you need some extra practice. I've got a combustion worksheet and I've got a precipitation worksheet. So you can work on these. The answers are on the back, and I'm happy to answer questions on them. But now we gotta do the chalk lab. So, before the chalk lab, very quick. Chalk lab is so quick. The main thing is to get it into the filter paper as speedily as possible. These are the lab partners. Up here at your station, you have two graduated cylinders, a large one and a small one. The large one is for measuring the substance that you need the larger volume of. The small one is for measuring the substance that you need the smaller volume of. You also have two beakers. That is where you're going to be running your reaction. I know it says test tubes. It really means beakers. You also have two funnels and two flasks. You should run both reactions at the same time. They do not take any time at all. You pour them together, the reaction happens instantaneously. You guys good?
Can you just repeat that one more time, please?
You are going to be running two reactions, one of them in one beaker, one of them in the other beaker. All you have to do is measure out the volume of the two things that go, like measure the calcium chloride for reaction 1, measure the sodium carbonate for reaction 1, pour them together into a beaker, put that in some filter paper.
And that's reaction 2?
That's reaction 1. Reaction 2, you take the same thing, but with different volumes. Calcium chloride plus sodium carbonate.
So that's just gonna
Mix
make
them together.
more.
I know. You're gonna have two separate reactions with two different volumes.
So the point of reaction 2 is just to make more of reaction 1?
You're gonna have two separate filter papers at the end, so you're gonna have two yields. You're gonna calculate the limiting reactant for both of those volumes. You're doing the same thing twice with two different
Okay.
volumes. Follow the instructions exactly. Not in trouble yet.
Do we have instructions or should we just look on?
I got them right here.
Bro, I want to. He started crying when I didn't.
You started crying?
Sean.
Why?
You want to.
Thank you.
Oh my, it's not my
Who's Kendall?
There's a chemistry.
Oh, yeah, I knew that. I knew that. I'm sorry.
It's okay. I'm also gonna give you some practice worksheets that you guys can just
Wait, you started crying when you told him that.
work on.
No, he keeps on. This is the 17th one.
Do you want me to turn this off?
Can I see
Yeah,
this?
thank you.
How do you?
Please just
Hold this.
I want to see something.
You press that button. Ion testing, yes.
So there's gonna be two reactions.
Two reactions.
Is that like the pre-lab lab?
Yeah.
Like, okay.
Alright, so if you have an ionic compound and you dissolve it in water, by the way, we have a guest in the classroom, the other Dr. Fisher. So,
Hi, Dr. Fisher.
alright, so if we have an ionic compound and we dissolve it in a solution, what happens to that ionic compound?
What was it?
Separate, like positive and negative.
Yeah, the ions separate into positive and negative. So if our compound is calcium chloride, CaCl2, and it dissolves in water, so CaCl2 is solid, dissolves in water,
We have CaCl.
what kind of Ca? Is it uncharged Ca?
Or
Wouldn't it be
Positive two.
positive?
Positive 2, and it's aqueous because it's dissolved in water.
Wait, so
Plus
why would it change from no charge to positive 2 charge when it goes in water?
Because they're
So
separate.
it always had that +2 charge, it was just canceled out by the Cl2,
Oh, okay.
or the Cl
Alright, yeah.
minuses before, and now it's separated out. And so what else do we have?
negative, like, is it negative?
Cl minus
1.
A 1?
minus 1,
If there's 2.
and there are 2 of them. Okay. Right? Okay. Sometimes I feel like I'm I make these practice problems and I'm like, this is great, this will show like 15 things all at once, but I actually only want to show you the one thing, and so sometimes my problems are not great there. I'll change it. 1 mole. Let's say that I have 1 mole of calcium chloride dissolved in 2 liters of water. So what is the molarity of calcium chloride?
It's just 1/2.
1/2.
1/2, right? 1 mole over 2 liters equals 0.5 capital M for molar.
What's the molar? It's liter. It's moles over liters. Mole per liter.
Yep. 0.5 moles per liter. You can always rewrite capital M as moles per liter. Yeah.
Is aqueous basically liquid?
It's not the same as liquid. Because it's not like I took this and I melted it with really, really high heat until it was like pure liquid. It's in a water-based solution. So there are ions surrounded by water molecules, which is different from being a liquid ionic compound. All right. Now what if I want to know the molarity of the Ca2+ ions in the solution? I know I have 1 mole of calcium chloride.
You put 1 mole of calcium over 2 liters.
Yeah, let's say, I'm going to do it the long way. 1 mole of calcium chloride for 2 liters times, what do I have to multiply by to get to
Ca.
a mole Ca?
Over the molar mass, is it?
No, what do I want to cancel on the bottom here?
CaCl2.
CaCl2. 1 mole CaCl2. Because there's 1 mole of calcium ions released for every 1 mole of calcium chloride equals still 0.5 moles per liter. Yeah? I'll switch colors. How about those chloride ions though? Because I want to know the molarity of chloride ions in solution. What am I going to start with?
1 mole of CaCl2 over 2 liters.
I'm way down the bottom board.
Times 2 moles.
2 moles of now minus over
1 mole of CaCl2.
equals 1 molar. 1 mole per liter.
Is it supposed to be 2 plus over the 1 mole of Ca?
This one?
Yeah, it is.
Yeah, that's a 2 plus. Sorry, doesn't really look like it, but it is. In the long week. Alright, so anytime you're working with ions in solution, you have to think about how many moles of ions are released when the ionic compound dissociates. And it's just the subscript that follows the ion. This is true even if it's a polyatomic ion. So if it was CaNO3 2 instead, then you could calculate the concentration of nitrate ions. Each nitrate is going to stay together as an NO3 minus 1. Alright. Okay, so why do I care about this? I care about this because a lot of reactions happen really well in aqueous solution that don't happen in solid state. So if I mix ionic compounds in solution together, I might get some kind of reaction. There's various types of reactions that you could get, and chapter 4 is all about all of those various types of reactions, but for right now we're only going to focus on one type of reaction that might happen. And that type of reaction is called a precipitation reaction. So this is what happens with a precipitation reaction. Okay. Okay, so this is a chart, it's in your reference packet. You have this chart and also on the same page a list of various rules for solubility. And what this means is that some ionic compounds are soluble in water and some ionic compounds are not soluble in water. So for example, table salt, soluble in water, but seashells, which are made of primarily calcium carbonate, not soluble in water. Right? That would be pretty bad for clams and stuff if their shells are soluble. A chart like this lets you know whether a compound is soluble or not soluble. So what you do is you find the cation on the top and then the anion on the side, and you match them up. And it says, all right, if what you got is sodium chloride, it's soluble. If what you have is calcium carbonate, it's insoluble.
Wait, so the
What is
stuff on top is
SO?
the liquid?
I think
The
slightly
stuff at the
solid.
top are the cations in the compound. The stuff at the side is the anion. So remember, each ionic compound has a positive part and a negative part.
So it's all separated into like solid.
No.
Okay.
We're considering only stuff in water.
What is the yellow one? Oh, slightly solid.
SL is slightly soluble, which means a little bit of it will dissolve in water, but not very much.
So NA.
Is this on our
Reference.
Yes, it's in your reference packet. Yeah. Any patterns that you guys notice?
The group 1 is soluble.
So this side is all soluble, so the group 1s are soluble.
Yeah.
What's this guy?
methane?
Oh,
Ammonia?
No, I was gonna say the pattern.
Yeah.
Oh, it gets like progressively more insoluble as you go down.
Yeah, they put the more insoluble things on that end of the chart. Any exceptions? Any anions that are always soluble?
ZN's 2+.
CH3CO2
2 plus? Well, not really, because there's some insoluble mixed solutions. But we've got the nitrates, NO3, always soluble. The acetates, CH3, CO2, always soluble. This isn't every possible ionic combination. This is just a subset that was convenient for plain scientific to put up here. You could have a more complete chart, but I'm not going to worry about you guys knowing the solubility of every single possible ionic compound. Yeah.
How can a compound not exist?
How can a compound not exist? It means that these two ions, they just don't associate very well together. If there's basically any other atoms in the area, they would rather react with those other atoms. They just don't mix
So it's
well
impossible
for
like
some reason. Yeah, they just
Okay.
don't mix well for
That's
some reason.
that's my question.
You can also think about it as a list of rules like this. You also have the same list of rules in your packet, and it's the same information. It just says that if you've got here's one metal cation, then it is always soluble and there are no exceptions to its solubility. These are soluble compounds and these are insoluble compounds. Alright, so why is this important? Well, this is important because you might be able to react some solutions and get an interesting thing out of it. I want this one. Alright, do you guys have a copy of the reference packet?
No.
The
Yes, some of you, does anyone need a reference packet? Alright, I think it's on page 11 on my version. Bookstore version somewhere.
Yeah, it's in my-
Alright, so let's imagine that we have nitrate, and a different aqueous solution that's made of ammonium sulfate, and we combine those two guys together. What is copper 2 nitrate? What is the formula for copper 2 nitrate?
What's dilute?
What is dilute? Dilute means that it's not very concentrated. So we're not adding like a ton of these guys together, we're adding just a smallish amount of these guys together. Yeah.
Cu2NO3.
Remember, what is this? The
See,
2 mean?
There's
The 2 means that it's got a charge of
Cu2 just.
No, see.
plus.
It says Cu2.
What's the charge?
Oh,
That's a
positive.
Positive
It's a
2.
transition metal. It's got a charge of +2 and nitrate.
It has -3.
Oh, well, it says
Oh,
Cu2.
nitrate.
Is it
Nitrate.
NO3 like parentheses 2?
It's
Yes.
-1.
Oh,
There's a
my bad.
There are 2 nitrates for every 1 copper. Don't get rusty on these. They are on the final for sure. Ammonium sulfate. What's ammonium?
NH4.
NH4. And sulfate.
SO4 2 minus.
SO4 2 minus. So what do I need to do?
You need to have 2 of NH4.
Alright, now if I combine solutions of these together, remember, really, if these guys are all aqueous, if these guys are an aqueous solution, these ions are separated from each other and bouncing around. And these ions are separated from each other and bouncing around in the solution. And so they can bounce into each other, and we could potentially have a reaction. So if this cation, the copper, wound up with this anion, what would that product be?
CuSO4 plus NO3 NH4.
Is that double displacement?
Yeah, double the
It is. It is. It's a double replacement reaction. The cations and the anions are switching places. Is it balanced?
Yeah.
Is it?
No.
No, it's not.
What do I need to do?
I put a 2 in front of that.
Alright, so this reaction could potentially happen. We could get these 2 products.
Wait, isn't it NH3? I mean NH4.
Yes, it is. Alright. This guy, is this guy soluble or insoluble?
Soluble.
How do you know?
Because
It says so on the.
it's soluble on the
It
thing.
says so on the thing. It's soluble, so what state is it going to be in?
So, the,
It's still going to be aqueous because it can dissolve and it's in water. How about NH4 NO3?
It is soluble as well.
It is also soluble, so it's also going to be aqueous. So nothing really happens. Great. 2 things mixed together and nothing much happened. That's exciting. Yeah, the bookstore version doesn't have the chart, it just has the rules.
Oh yeah, can I also have one of those?
For this lab, are we working in partners?
Yes. Partners and wonders of three. Alright, let's try again. Let's do iron 3 chloride. What's iron 3 chloride?
Fe2. No, Fe3.
FeCl3.
Fe3 plus.
FeCl3.
Yeah, it's Fe3 plus and each chloride is -1, FeCl3.
Wait, oh
How about silver nitrate?
Oh,
yeah.
it's like
AgNO.
NO3.
Alright, if these cations and anions switch places, I'm gonna get what?
FeNO3 plus Cl.
Wait, why are you multiplying it by 3 again?
Because each nitrate has a -1 charge, and this iron 3 has a +3 charge, so I need 3 nitrates to cancel out the +3 from the iron.
Why are we replacing them when we put them in
But
water?
then wouldn't that leave us with
When they go in water,
6
they
of
break up
NO?
when they're separately.
No.
So they
Yeah.
always, whenever you put it in water, it always breaks up and goes
Yep.
to the other person.
If they're soluble, they break up. All of those ions bounce around. And what happens when these Fe, well, let's finish. I mean,
AgCI3.
AgCl. And I'm just gonna go ahead and balance it real quick here. Like that. Aqueous. Aqueous. Alright, this FeNO3, is that bisoluble?
It is soluble.
It is
How do you
indeed.
know it's soluble? You check the chart.
It's soluble.
Check the chart.
It's aqueous.
I don't
Check the
have.
chart. How about this guy?
It's insoluble.
Insoluble. Oh my god. This guy can only be a solid. So what happens is you mix two solutions together, two homogeneous solutions together, and a solid came out of it.
Is that like the
precipitates.
crystals?
Yeah, they're tiny, tiny crystals. They're generally so tiny they look like powder. So this is called a precipitate. It's a solid that rains out of solution because you've formed an insoluble compound. The Ag ions and the Cl ions knocked together and they stuck. And they stuck so strongly that the water couldn't break them apart, and so they fell out of solution as a solid. Mixed together two solutions, got a solid out of it. That's a precipitation reaction. Alright. Alright, so this is the total overall reaction for what's happening. But really in reality, FeCl3 minus are a bunch of ions knocking around in solution. And this is a bunch of ions knocking around in solution. So we can actually write it that way. This is called the complete ionic equation, and this is the only time I'm ever going to write a complete ionic equation, because they are tedious. This is what is happening to all of the ions in this solution. FeCl3 is aqueous, so in solution, it's going to be two ions. What are the two ions?
Fe.
Fe with what charge?
3 plus.
3.
3 plus. Plus
3 Cl.
3 Cl minuses. How about that AgNO3? That's going to be two ions, Ag, and there's 3 of them in this
Ag3.
formation.
Plus NO. Wait, 9 NO? Would that be 9 because there's 3 and 3?
So the NO3, the whole NO3 stays together as one ion.
So it's not
But
impacted by
there
the
are 3 of those,
Three
just
NO3s.
3 NO3, 3
Oh,
NO3
so three
minuses. I wish the arrows lined up, they don't. Alright, this FeNO3, what is this guy in solution? 2 ions, Fe3 plus. Plus how many NO3s?
3 NO3s.
3 NO3s. They've got a minus charge. They are aqueous. Whew, plus.
3 AGs.
Now remember, these guys are not ions. They are together as a solid compound.
So
The
3
Ag and the Cl are glued together by an ionic bond.
So
That's
3
tight.
AgCI. What's that
This
on
is
the
a solid.
How do we know if it's a solid?
You know that it's a solid because it is the one thing, the one combination of ions that is insoluble. When you look on the chart, AgCl does not dissolve in water. Yeah.
If I was like looking at this equation, how could I tell that 3 AgCI was a solid? Not a solid, a
You would
compound.
you need to look at your chart, your solubility chart, and when you pair up silver and chlorine, those two make an insoluble compound.
What
So
page
because-
is the chart on?
11.
And how do we know which one like changed? Why does iron not change?
Because the iron is associated, the iron chloride is soluble, and the all iron nitrate is soluble, so the iron just stays in solution. It doesn't find any ions that it hooks up with so strongly that it can't dissolve. Okay.
What is this equation for? Like, what do we?
So this equation is the equation that includes all of the ions. But really we don't actually use this form of the equation very much. Why? Because nothing happened to the iron. There's iron on the reactant side and also iron on the product side. So it actually just cancels out. The iron is what we call a spectator ion. Iron 3 is a spectator ion.
Should we write that in our reaction too? Or is that, oh, wait.
That is a definition. That is a definition. What do you think is the other spectator ion? An ion that does not participate, it is on
Yeah, no,
both
here.
sides.
Copper.
The NO3 is the other spectator ion.
I tried.
Because it's on both sides of the arrow. Nitrate is also a spectator ion. Nothing happens to those ions. They don't participate in the reaction. They're unchanged by the reaction. They don't even know that it occurred. So, this is the complete ionic equation. I don't really care about the complete ionic equation. What I care about is called the net ionic equation. You guys know what net means? It's not the internet,
It's the total.
it's the total.
Oh.
It's not a fishing net, it's the total ionic equation. It's the overall equation of the actual ions that are actually participating in the chemical reaction. Two aqueous things that come together to form a solid thing, and that solid thing comes out of solution. So our net ionic equation here is Cl minus plus Ag plus yields AgCl solid. I just canceled out the 3's because you can.
Wait,
This is what's actually happening. Chloride and silver are coming together and forming a solid. The iron and the nitrate aren't participating. They're there, but they don't participate in the reaction. This is the net ionic reaction. Just the ions that are involved in making the solid precipitate.
okay, that makes sense. Wait, so would it not be Cl3 on the left side?
I kind of skipped a step, so it's 3Cl plus 3Ag equals 3AgCl.
Oh, so you
So we can just
simplified it?
take, I just took all the 3's out for making it simpler.
So, wait. So we have the two compounds and we're mixing them. And then that's this one is the total overall reaction Okay,
of our two compounds combined. We get two possible products.
okay.
But the iron and the nitrate ions, they're not doing anything.
Okay.
They're spectating, they're just watching.
Okay.
So they're spectator ions, so we can take them out of the whole everywhere. And we're left with just the net ionic equation. I do want you guys to be able to write a net ionic equation.
How do we identify? Oh,
Do not care about the complete ionic equation. I only care about the net.
Do we have to do the complete ionic equation to get to the net ionic?
Good question. No, you don't. Because I can say, look, I've got AgCl, that's my only solid. What are the ions that made up that AgCl? They were Ag and Cl minus. Ag plus and Cl minus.
Okay.
You don't have to actually write down all of the ions and cancel them out. You can just see, like, okay, the iron is here, the iron is over here, it didn't participate.
And why for this equation do you instead of use like the I forget what they're called, like the subscripts, and instead like put the like the 3 in front? Like
This one?
Yeah.
Yeah, because in solution, it's not 3 Cls in solution. In solution, it's gonna separate out. You're gonna have like 1 iron and 3 chlorides. And when they're in solution, there are 3 totally separate chlorides and 1 iron. Does that make sense? They're not related to each other anymore. They bounce away from each other. They're not connected. And the subscript implies that they're connected. All right. Golden. So,
What if you have a all aqueous product? Can you write a net ionic
you
equation?
cannot, because nothing happened. There was no reaction. Yep, so in this case, there is no net equation. There was no reaction. Nothing happened. All right, can I erase? Okay. Whew. So, just like we can do, Alright, so with the precipitation reaction, we can do stoichiometry, just like we can with any other reaction. I'm going to skip ahead to this guy. Okay, we've got solutions of sodium hydroxide and iron 3 nitrate. When they're mixed, we get a red precipitate. I want the net ionic equation for the reaction, but then I'm going to use that to find how much product we get. Okay, so we can take this step by step. First of all, we got sodium hydroxide and iron 3 nitrate. Sodium hydroxide,
NaOH.
NaOH, plus iron 3 nitrate, we just did that.
Fe3, NO3.
NO3.
Like 3. Yeah, 3, that's what I said.
What are our 2 possible products?
NaFe.
And
Nope, nope.
You can't do
NA.
that.
Can't put the 2 cations together.
Oh, Na.
NaNO3 plus.
FeOH.
How many OHs?
1.
3. Iron is a 3.
OH minus is -1, and there are 3. I know you guys might not have memorized these subscripts. That's okay.
Oh, wait, no.
Yeah.
What's the definition of cations and anions again?
Cation is positively charged, anion is negatively charged.
Okay.
Because cats are good.
Like cations are positive charged?
Positive.
Okay.
They're
Dog ion.
positively charged. 'Cause they pause. That's right, yes. Oh yeah, well, let's balance this. Balance this puppy.
3. Like 3.
3
You're
here.
gonna put 3 on the NA.
There we go.
Yeah.
3 here. There we go. Alright, NaNO3. Is that soluble or insoluble?
Is there any way to know without looking at the reference packet?
Solid.
You can. I
It's
think it's
soluble.
good to remember that group 1 metals are always soluble and NO3 is always soluble. Those guys come up a lot, and it's just convenient to know.
It's soluble.
It's soluble. And NO3 is soluble. Group 1 metals soluble. Together, definitely soluble.
It's insoluble.
It's got insoluble. Thank you. Solid. Alright. So I told you I'm never going to write a complete ionic equation again, so I'm not going to, but I do want to write the net ionic equation.
So it's Fe plus NaOH. Fe plus OH or NaOH? Oh, OH. And then FeOH.
Balanced? key for balancing, same number of atoms on both sides, also same total charge on both sides. Now I have charged things. This is a +3, this is -1 times 3 minus 3. 0. Okay. Alright, so now here's a hard question. I'm just going to ask this question straight up. I want to know how many grams of precipitate are formed, how many grams of this puppy are formed, when you mix 50 milliliters of 0.2 molar NaOH and 30 milliliters of 1.25 molar FeNO3.
What?
So,
So we're taking two things. We have known concentration, known volume of both things. We're mixing them together. The reaction happens and a precipitate comes out. This is the type of question that I'm going to ask you on the upcoming test, and also the type of question that would be on the final. That's why I'm jumping straight to it, because we got limited time. This question is a limiting reaction problem.
It's a what?
It is a limiting reactant problem.
Wait, is that the one with the?
Guys remember limiting reactant problems?
It's the one where like one substance can only have a max number, so that they can't produce any.
No,
My mom thought it was
you're not
so
supposed to
funny
just
when
pour it
You
in.
guys stopped at the dance studio.
Yeah, we
You guys
are.
were like,
They are.
Oh, you
Mix
are?
the two
So
solutions.
this is reaction 1, we're mixing,
No, but then what about like the filter paper and stuff?
yeah.
Okay, never mind.
That's after.
That's to find out actually how much you need.
glorious. Reaction 1.
Do you want me to
Yeah, you
do-
can do the 5
Is it-
milliliters.
So weird. Like,
Reaction 2.
We need to filter them into these.
What?
Glammy glammo.
Oh,
Less cloudy.
we did that already?
Two beakers?
Yeah.
Beautiful.
25.5?
Be filtered.
So, after they've been filtered, this is what they look like. This is reaction 1. Got some cloudy stuff at the bottom because the chalk dust is so fine, a little bit of it can make it through the filter paper. And here's reaction number 2. And it's also got a little bit of cloudy at the bottom and chalk dust on the inside of that filter. There you go. Chalk.